Good evening, everyone. Uh, my name is Aditya Sharma, and this is the fundamentals of compressible flow course being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program. And this is the last week related to this course, fundamentals of compressible flow. So it was a 12-week course, and we are into the last week of this course. So in the last in week 11, we discussed measurement diagnostics, and here also we'll be continuing with the same topic. Okay, so there we focus on subsonic flows. Yes, so we saw the subsonic wind tunnel we discussed there majorly. And here for supersonic flows, hypersonic flows, and hypervelocity flows. So we'll see what kind of setup we use in these cases. The instructor for the course is Professor Niranjan Sahu from Department of Mechanical Engineering, IIT Guwahati, and I'm a teaching assistant and research scholar here at Mechanical Engineering Department 20. So we shall wait to see if somebody joins. After that, we can start with today's session. Also, this is not the last session. So, last session will be on 14th of April, where we will be concluding the session. Briefly, we'll try to revise the topics that have been covered in different weeks. This is it. Let's wait for a few minutes to see somebody comes. Okay. Okay, so we can start with today's session, measurement diagnostics and experimental facilities for compressible flow. So two lectures are there. Okay, lecture number 29 and lecture number 30. Okay, where topics have been discussed. So these two lectures are there. And lecture number 31 is also there where shock tube setup has been explained. So that I'll leave to the lecture video only. So we'll be discussing lecture number 29 and lecture number 30. So you shall see topics and then questions related to each lecture. So we'll start with the lecture number 29. So aerodynamic test facilities, lecture number 29. Here we have started with compressible flow regimes. So first, if your Mach is less than 0.3, we call such flow as incompressible flow. The density variations are not considered significant. Then if your Mach is greater than 0.3, okay, and this is within your 0.8 Mach, we call it subsonic. Yes. Now, if your Mach is between 0.8 to 1.2, we call such flow as transonic. Why transonic? Because transition is taking place from subsonic to your supersonic flow. Okay. Then Mach 1.2 to 5 we consider as supersonic. And if your Mach is greater than 5, we call it as hypersonic. Right. So these are the flow regimes. Okay. So then in the last lecture, we have seen hypervelocity flows also. Okay, so we saw suborbital, then superorbital, then escape. So we saw this. This is less than, this is greater than this. This is around 11.2. 1 second. So this is the okay. Uh, yes. So now in relation to your compressible flows, so if you see your lecture number 29, so in slide number 5, we have been shown so different speeds have been given and then your power requirement has been given. Okay. And how the length scale is related to your power requirement. Yes. So this has been shown. And how your velocity is related to your power requirement. So kinetic energy is given this way, right? Now for mass, we can write it as rho AL. Okay. So mass I have written as this, right? So AL is your volume and rho is your density, right? Now time you can write down as this length by your velocity. Now rate of energy flow, which we also call as power. So this you can write down as and which will eventually become so your power requirement to accelerate this mass is proportional to your velocity, right? In this way. So this is there. Then briefly, we have been introduced to shock tunnel. Okay. So its schematic I'll draw later. So this is used for your hypersonic flows. Now we know what are hypersonic flows, where Mach is greater than 5. And there are expansion tunnels, which can generate hypervelocity flows. So this is there. Okay. Then is your supersonic wind tunnel. So the schematic of your supersonic wind tunnel goes like this. Initially, you have a reservoir where you have some gas and pressure, pressurized gas. Then you accelerate it through a nozzle. Okay. So this is your reservoir. This is your nozzle. Then comes your test section where you will keep your aerodynamic model. Okay. So this is your test section. The flow is moving in this direction. Okay. Here your Mach is obviously greater than 1 because we are talking about supersonic wind tunnel. Then you have a diffuser here. Then at last you have exhaust. So at reservoir, stagnant conditions are there. At your nozzle, your Mach is roughly equal to 1 at the throat. Then at test section, your Mach is greater than 1. Then at diffuser, again, your uh, flow is decelerated. Okay. And eventually it is exhausted to your atmosphere. Here also your Mach is. So this is about your supersonic wind tunnel. Then your intermittent in-draft tunnel has also been, schematic of it has also been given. So intermittent basically means this tunnel is not continuous, right? So here first we have a storage tank. Okay.
Then we have valves. Then we have a settling chamber. Okay. After that, we have again nozzle like we had in previous case. After nozzle, we have test section. After test section, we have diffuser. Then at the end, we have a silencer. So after your diffuser, if you are not having a silencer, so it creates a lot of noise. So your supersonic wind tunnels. So like when I was doing my master's in BIT Mesra, so they have two supersonic wind tunnels, and when they would operate these supersonic one of the supersonic wind tunnels, so it would, because they did not have this silencer, so this would create a lot of noise in the whole lab, right? So this is there. Okay. After this, the topic moves on to, high enthalpy impulse test facilities. Okay. So power requirement we have seen. So it increases with cube of velocity. Okay. So as speed increases, your flow establishment time and test time decreases. So test time is the amount of time for which you want to run the facility to get useful data, right? For your analysis, so that you're able to do proper analysis of the flow physics, right? Then establishment time is there, the time your facility takes to establish a meaningful flow, right? So this, as you increase the speed of the flow, right? So if you increase the power, right, and then increase the speed with that, So establishment time also decreases because your flow is moving too fast, right? And then the test time also decreases. Okay. Then there is one term which is body pass, BP. So this is the ratio of your test time to your flow establishment time. Okay. So for your laminar flow, so this BP remains if it is in the range of 3 to 4, so this is considered good. For your turbulent flows, so your BP has to be, we want more test time in case of our turbulent flows. We want the BP to be 20, around 20 to 50. Okay, so we want more test time. So this is there. Then moving on to shock tunnel. So I'll draw the schematic of shock tunnel. So this is your driver section. This is your driven section. This is your CD nozzle. This is your test section. Then this is your dump tank. This is your vacuum pump. So I was telling initially that your shock tunnels are used to generate hypersonic flows. Okay, so this is the schematic. So this is your aluminium diaphragm, and here you have a paper diaphragm. So now what will happen here? So these are tubes basically. Okay, so this is a hollow tube. Driver section is a hollow tube. Then, so this one plane we are showing here, right? So this is a tube and it's one plane we are showing. So this is your driver section. Okay, this is one tube. Then driven section, right? Then you have your CD nozzle. Okay, so these are kind of conical shapes, right? Horizontally we have kept. Yes. And from here to test section will again be we can keep it cuboidal also, right? So what we will be doing is we will pressurize this driver section first, right? And your driver and driven section will be separated by a diaphragm, right? So imagine there are two tubes, right? Connected, right? And in between these two tubes will be keeping one sheet that will separate these two sections. So one sheet will be of aluminium. That is what we are calling as aluminium diaphragm, thin sheets. Okay. Then between your driver section and CD nozzle, we will be again keeping one thin sheet, right? That will be of paper. So now what we will be doing is we will uh, pressurize this driver section with some gas. Okay. So we'll keep on pressurizing this. So eventually what will happen, your diaphragm, this aluminium diaphragm is going to burst. Okay. Then this is going to give a shock, right? And behind the shock, you'll have gas moving along with it, right? So your shock is moving in this direction, then gas is also there. So this shock is going to strike your paper diaphragm. It's going to burst, right? Then again, you're going to get the shock here from paper diaphragm, and this is going to propagate in CD nozzle, and eventually you'll have this hypersonic flow in your test section, right? And then there is a dump there for the gas to eventually go in it, right? So this is your shock tunnel. I hope this is clear. Then there is Ludwig tunnel. So let's draw the schematic of it. Now what happens here? So again, you're having a tube like structure. Okay, storage tube you have, which is connected to your nozzle, right? Then you have test section and then you have dump tank. So if we see the shock tunnel and Ludwig tunnel, so here in Ludwig tunnel, you're not using a diaphragm, okay, to generate a shock. You basically are using a fast acting valve, right? So this fast acting valve basically is going to, so you'll have this pressurized tube, and then you'll have this fast acting valve which will open. Okay, this is going to give a shock. So with this shock moving in downstream direction, in upstream direction you have, so in this direction you'll have expansion wave, right? So what limits your test time here is that you'll have this expansion wave moving in this direction. So it will reach at this wall, it will get reflected, and then it will interfere in your this moving from nozzle to your test section. It will go there, right? So till the time it has not reached our test section. So that is the meaningful time that we have to perform our tests. So this is your Ludwig tunnel. Okay. Then we have pre-piston shock tunnel. So its schematic is this way. So first you have a reservoir tube. Then you have a compression tube. So this basically is your piston. This is your compression tube. Then we have low pressure driven gas. Then we have nozzle. Then we have test section. Now, how this works? So you have a reservoir tube, okay, where you'll be having compressed air. Your compressed air is used as reservoir gas. So this compressed air is going to push your piston, okay. Then in your compression tube, argon mixed with helium is preferred as driver gas, okay. So here you are going to have your primary diaphragm, first diaphragm. Then here you are going to have your secondary diaphragm. So like we had in shock tunnel, first we had an aluminium diaphragm, then we had a paper diaphragm. So same way we'll have some primary diaphragm here and in the compression tube. So through your piston, this will be compressed. Okay. And then your primary diaphragm is going to burst. This is going to give a shock. So this shock will eventually this burst this second diaphragm. And from there, the flow is going to move on to your nozzle and then reach the test section. So this is your free piston shock tunnel. Okay. Then we have gun tunnel. So let's see gun tunnel. Let's draw its schematic. So this is your driver tube. This is your piston. This is your low pressure driven tube. This is your nozzle, and this is your test section. So this setup is used to produce hypersonic flows. So what will happen here? So you have a driver tube, then piston, then low pressure driven tube, then nozzle, then test section. So you will first pressurize your driven tube. So this will move your piston, right? So this will accelerate your piston. This is going to give a shock here in front of piston. Okay. So which will hit your diaphragm. Okay. So this shock will hit your diaphragm and then it is going to reflect back, right? Now this hitting of this shock is going to burst this diaphragm. Yes. From here starts our testing of the meaningful duration for our testing, right? So this burst will again lead flow to test section, right? So this is there, but then this shock that has generated from the piston, right? So this has or this pressure wave that has generated from piston, this when reflects from the diaphragm, right? So it will move towards piston, right? And moving towards piston, again it will reflect from piston towards your nozzle. Okay. So once it's this pressure wave reaches the nozzle, right? So till that time, you have your uh, meaningful time that you can use as your test time, right? So the time from where this pressure wave from piston strikes the diaphragm, right, to the time when it reaches piston, reflects from there, and then reaches nozzle. So till that time, you have this meaningful test time, which you can use for your experiments. So this is your gun tunnel, right? Then we have expansion tunnel. So let's draw the schematic of expansion tunnel. So reservoir tube, then piston, compression tube, this is low pressure driven tube, this is acceleration tube, this is nozzle, this is your test section. Here you have your primary diaphragm, Here you have your secondary diaphragm. So different types of setups till now we have seen. So your expansion tunnel somewhat looks like your pre-piston shock tunnel, right? But one change is there in expansion tunnel. That is your acceleration tube has been added. Okay. So what is this acceleration tube? So this is a region which is evacuated to a very low pressure of 10 to 100 pascals. Okay. And this change gives you hyper velocity flows. Okay. So this is your expansion tunnel. So now we'll move on to questions. Okay. So this we saw. Now we'll see questions. But before that, let's take a short 5 to 10 minutes break. After that, we will continue with the session, right? Okay, so let's continue with the session. So first question says that, please read the question. So this is about transonic flows. So which of the following is correct about the Mach number of transonic flows? Yeah, B is transonic. Okay. So B is the correct answer to this question. Then next question, let's see. Shock tunnels are used to study flows in which regime? So if you see shock tunnels, so they are used to study hypersonic flows. So this is your shock tunnel where you have a driver section and a driven section separated by an aluminum diaphragm. Then the driven section is connected to a CD nozzle. Then CD nozzle is connected to your test section. And at the end, you have a dump tank. The driver section and CD nozzle are separated by a paper diaphragm. So you pressurize the driver section, you burst the aluminum diaphragm, you get a shock. Then from here, your paper diaphragm bursts. Again, you get a shock. This travels in your test section and then to go to your dump tank. So this is your shock tunnel. So hypersonic flows. Expansion tunnels are used to study dash flows Transonic, supersonic, hypersonic, hypervelocity. Expansion tunnel, the expansion tunnel. So we have seen that it is used to study hypervelocity flows. Now what is expansion tunnel? You have a reservoir tube, okay, where you'll have pressurized gas that is going to move your piston. Then you have a compression tube, like we had in free piston shock tunnel. So then you have a compression tube. This compression tube is separated from your low pressure driven tube by primary diaphragm. Then your low pressure driven tube and your acceleration tube are separated by a secondary diaphragm. Your acceleration tube is evacuated to a very low pressure of 10 to 100 pascals. Then your acceleration tube is connected to your nozzle. This nozzle is then connected to your test section. So expansion tunnels are used to study hypervelocity flows. Question number 3. Then next question. So please read the question and try to answer this. This is about supersonic wind tunnel. So now let's see supersonic wind tunnel. So options are given: D level nozzle, diffuser, storage tank, none of the above. So you have a reservoir, or which we can call as storage tank. Okay. Then we have a CD nozzle, D level nozzle, which we can D level nozzle we can call. Right? Then we have diffuser also here. So question says that which of the following is not a component of supersonic wind tunnel. So all three are components of your supersonic wind tunnel. So D option will be correct. There is no such option which is not a component of supersonic wind tunnel. Okay, there should have been D, I believe. All right. Question number 4. Then question number 5. Says that question number 5 says that the power requirement in aerodynamic tests increases as square of velocity. So we have seen here the power requirement we have seen. So this is cube of your velocity. Okay. So power requirement is cube of your velocity. Now you must have understood. So where this area and length, these entities where how they are related to your this calculation. Okay. Because we are using tubes in our setups, right? So keeping that in mind, so these calculations have been done. So this expression has been derived. So this is how this is related as cube of velocity. Power requirement in aerodynamic tests increases as cube of velocity. So this is a false statement. Question number 6, then it says that real gas effects become prominent in wind tunnels as specific heat varies in terms of both temperature and pressure due to association of chemical reactions. So whether this is correct or not. So please try to answer this. So real gas effects become prominent in wind tunnels. So with respect to your wind tunnels, whether this is correct or not, and in your wind tunnels, does your specific heat ratio vary? So this statement, if you see, is related to your lecture number 29. If you see in your slide number 16, you'll find this statement. So this statement is related to your shock tunnels. Okay. So real gas effects become prominent in shock tunnels because here your specific heat ratios start to change with temperature and pressure. Okay. Because chemical reactions are involved in such high velocity flows. So this is a false statement. Okay. Because this is not related to wind tunnels but related to shock tunnels. And based on Ludwig tunnel, please see if the statement is correct or not. Now going to Ludwig tunnel, driver section and driven section. This is the question says that the driver section and the driven section are the key components of a Ludwig tunnel. So we're looking at the so if you see your Ludwig tunnel, there is one single tube only, which is being pressurized. There is no driver and driven separate tubes. There are no such tubes. Okay. So in that case, this becomes false statement. A gun tunnel is used to produce hypersonic flows having high stagnation pressure and moderate stagnation enthalpy for intermediate altitudes. Question number 8, related to gun tunnels. So whether this is correct or not. Please try to answer this question. So this is a correct statement. Okay, so gun tunnels are used to produce hypersonic flows. Okay, so this is a true statement related to your gun tunnels. Question number 8. This is your gun tunnel where you have a driver tube, a piston, a low pressure driven tube. Okay, a diaphragm you have, then a nozzle, then a test section. Right? Your driver tube is pressurized, moving your piston. This piston is giving a pressure wave that is going to strike the diaphragm. The diaphragm is going to burst. Your test time starts. This pressure striking the diaphragm reflects, strikes the piston, then again reflects, reaches the nozzle. And when this pressure wave reaches the nozzle, your test time stops. So this is your gun tunnel used to produce hypersonic flows. Then question number 9. In an expansion tunnel, an unsteady expansion gets propagated downstream of the secondary diaphragm location, which enhances the total enthalpy, total pressure, and total enthalpy of the shock heated test gas. So whether this is correct or not. So the unsteady expansion gets propagated. This is upstream. Okay, not downstream of the secondary diaphragm. So if you see your expansion tunnel, so this is your secondary diaphragm, right? So your expansion wave will move upstream, not downstream, right? After the burst. Your shock is going to move in the downstream direction. So in that case, this becomes a false statement. Then next question is there, if the velocity to be achieved for an aerodynamic test is 2000 meters per second and the length of the slug is 2 meters, find the flow establishment time of the facility. So flow establishment time is equal to L by U. So this is going to be, that is 1 millisecond. So for 2000 meters, that is 2 kilometers per second of your flow velocity. And the length of the slug, 2 meters. The flow establishment time is 1 millisecond. Then lecture number 30 is there. So in lecture number 30, we start with compressible flow theory. So normal shocks, oblique shocks, expansion waves. So all this has been again revised in few slides. Okay. Then comes shock tube, its characteristic features, design of shock tube, theory of shock tube. Shock tube available at IIT Guwahati. So I personally work with the shock tubes in the facilities available here. Okay. So I have designed also shock tubes for my study here in the gas dynamics lab. So this is shock tunnel, and then compressible flow and shock wave research. So this is there. So focus here is on shock tubes. Lecture number 30. So I'll tell you about the shock tubes we work with. This is your gas cylinder. So two gases we use, one is helium, one is nitrogen. Okay. So what we do, so these are two hollow tubes, right? And then this driver section is pressurized given this gas. Okay. Diaphragm we use, aluminum diaphragm, mylar sheets, paper diaphragms we can use, right? So at some pressure, this diaphragm is going to rupture. Okay. This is going to give a shock, which will move in this direction. Now, one thing is that you have a shock, but then there is gas also. So there are two things. One is your shock, one is your gas. So in front, you'll have shock moving, but then here, this is your, sorry, this is your contact surface. Contact surface, what is contact surface? The contact surface that separates your driver gas and your driven gas. So you have gas in driven section, you have gas in driver section, right? So this, when this gas moves, first your shock wave will move, right? And then gas will come after some time. It's not that the gas and shock are moving together. Okay. So this is your contact surface. And in this direction, from diaphragm, in the upstream direction, you're going to have expansion waves. Right? So this is there. Now in your shock tubes also there are regions defined. So this is region 1 behind the shock, this is region 2, this is region 3, and this is region 4. So this is there related to your shock tubes. Now regarding the instrumentation, what we do. So first we'll keep one pressure gauge here to see the burst pressure, right? Because from P4 by P1, so this is region 1, this is region 4, right? So from P1, we can get, so from this ratio, we can get Mach. From P4 by P1, we can get theoretical Mach number, right? Then we keep two pressure sensors here. Okay. So your shock will come in this direction, will pass through pressure sensor 1, will pass through pressure sensor number 2, right? So the distance between these two pressure sensors we know. Let's say this is X is this distance. Now we know at what time the shock has passed through pressure sensor number 1, at what time it has passed through pressure sensor number 2 when we acquire the data. Okay, and distance we know. So this distance by time can give you velocity, right? And now when you divide this velocity with your acoustic speed, this can give you eventually Mach. Right? This is about Mach. Then what we can do, shock tube, we can mount a model here. At the end, this is driver, this is driven, this is your end flange. I hope you understand what is a flange. Nothing but a circular plate, right, at the end of this tube. One flange is here, right? One flange is at the end. So here we can fix a model and we can have instrumentation on these models, right? We can keep force sensors, accelerometers, we can keep on this model and then we can try to study. So when your shock hits this model what happens, right? So such studies can be done. And then there are unconventional uses of shock tube also, right? So that is there. And in these unconventional uses, one is to use your shock tubes for your underwater blasts. So that basically I'm studying, right? So this is about your shock tube. Then moving on to questions. So shock tube is an impulsive device used to create short duration forces and heat loads. Whether this is correct or not, this is a correct statement. Okay. Then moving on to next question. In a shock tube experiment, nitrogen at 288 Kelvin is used as driver gas, leaving driven section as air. Two high frequency pressure sensors mounted along the driven section give two near step response at intervals. Find the shock Mach number if the distance. So this is there. So let's do this question. So I've already explained how we can get Mach, right? So question number 12, solution. So velocity you can get as distance by time. Distance between two pressure sensors. If you see this figure, distance between two pressure sensors is 0.3, right? And then time taken to move from one pressure sensor to two for the shock is 0.513 millisecond. 0.513 into 10 raised to power minus 3. So this becomes 584.79 meter per second, right? Now, acoustic speed is R is 297 given, T is 288 given. So if you calculate this, this will come out to be this much, right? Then your Mach becomes this becomes around 1.69. Right, so this is it about shock tubes. So we have come to the end of this session. So then I'll conclude the session. So we started with supersonic wind tunnel. So different types of setups we saw. Okay. For different types of flow regimes. So shock tunnels for supersonic flows. Sorry, supersonic tunnels for supersonic flows. Then shock tunnels, supersonic wind tunnel for supersonic flows. Then shock tunnels for hypersonic flows. Yes. Then gun tunnel also is used for hypersonic flows. Yes. Then we saw Ludwig tunnel also, free piston shock tunnel, right? Then expansion tunnel we saw. Expansion tunnel is used for your hypervelocity flows. One change here in expansion tunnel is that we are using acceleration tube here. So if we compare this with the free piston shock tunnel, so acceleration tube has been added here, right? So this was your first lecture. Then there were shock tubes, okay, which again are used to study supersonic flows, right? Where we have a driver section and a driven section separated by a diaphragm. We pressurize the driver section, the diaphragm bursts, we get a shock, right? So this was there, right? So this is it about week number 12, right? The next session will be on coming Tuesday from 6 to 8 p.m., where we will be uh, concluding this whole course. So thanks for watching this session. Thank you.